All right, everybody, let's work some examples that involve momentum. So here's our first one. I'd like for you to, for each one of these, pause the video, see if you can work it out yourself, and then we'll work it out together. Our second one involves a clay and a ball hitting the back of a car. Our third one, we have two masses held together and then a spring between them, and you cut the string. Our fourth one involves some graphs, and our fifth one as well. And then these last three involve momentum and energy and other parts of physics. These are likely to be the kind that you see on the AP exam. This thing right here is called a ballistic pendulum. A ball is shot into a pendulum. They stick together and then the pendulum swings upward. In this one we have a collision and then these two blocks slide up this hill. And in our last one, we have a ball that rolls down, collides, and then they go off together and land on the ground. So you can see some 2D motion in this one. All right, I want you to pause the video, and then I want you to try to work these out, and then we'll work them out together. All right, everybody, let's work some problems. Here's our first one. And in this particular one, we have two spheres that collide. The force between them is shown in this graph. It's a force time graph, so this will be impulse. What is the final velocity of each sphere, and how would you find out if the collision is elastic or not? So first thing, we know that this area right here will be the impulse. So F delta T will equal, hey, be careful, that's 4, that's 15, so that's, what will that be, 30 Newton seconds. So that may come in handy later. Okay, find the final velocity of each of the spheres. Well, they're colliding, so this seems pretty straightforward, doesn't it? It seems like we should just do conservation of momentum.
Initial equals final, so that would be mv plus mv. I'm going to call this one here 1 and this one here 2. So that would be 1, 2, initial equals mv plus mv, 1, 2, but that's final. So I put in 10 times 2. I'm neglecting my units right now. And, oh, be careful, that's a negative 2 right there, right? So that's plus 8 times negative 2 equals 10 times the final velocity plus 8 times the final velocity for 2. All right, so this ends up being, what is that? That's 20, and that is negative 16, so that would leave us with 4 equals 10 v1 plus 8 v2, and those are the final velocities, and...
Drat, we have two unknowns. That's a problem. So, I think we're going to have to use this graph after all.
So we know that F delta T equals the change in momentum. And, well, we have two of them that are going to have a momentum change, right? So I'm going to, well, we better write down which way these impulses are, okay? So when they collide, this one's going to get an impulse to the right. This one's going to get an impulse to the left. F delta T, correct? So this will be a positive impulse. This will be a negative impulse. That's super important, or otherwise we're going to end up with some issues. So I'm going to take this one, all right? So my impulse will be a positive 30 Newton seconds. This will be plus or minus, depending on which one we're talking about. And so that's mv final minus mv initial for this one. So my mass, of course, is 8. My v final, I don't know, minus my initial, which was a minus 2. So I'm going to get 30 equals this. All right, and when I do the math,
I get that this final velocity for 2 equals 1.75 meters per second. All right, and that is positive, so it means to the right. So that means this one hit and turned around. Okay. Now let's find out what our velocity is for the other one. And since I already have this equation, I'm just going to plug this in.
And I end up with 4 equals 10 v1 plus 8 times plus 1.75.
And so v1 turns out to equal negative 1 meter per second. So that one turns around. So they come in with 2 apiece, and they turn around. And hey, I want you to notice this goes from negative 2 to positive 1.75. This one goes from negative 2 to negative 1. The smaller one has a greater change in velocity, and that makes total sense because it has less mass. Therefore, for the same force, remember Newton's third law, or for the same impulse between them, the 8 kilogram will have the greater change in velocity. What kind of collision is this? Is it elastic or not?
To be elastic, the kinetic energy 1 must equal the kinetic energy 2, or the initial must equal the final. I want you to notice that kinetic energy is 1/2 mv squared, right? So I could figure out 1/2 mv squared for both of them initial, and I could compare it to the 1/2 mv squared plus 1/2 mv squared for both of them final. But let's use our brains.
notice that the masses don't change in the collision, but the velocities do. We had a 2 here initially and a 2 here initially for this one. And afterwards, we end up with a 1, negative 1, it won't matter, it's squared, and a 1.75. Do you see that this number over here is going to be smaller? So our final kinetic energy is less than the initial kinetic energy, so it is inelastic. Okay, in our second problem, we have a lump of clay colliding with a toy car and sticking with it and them going off together, or a ball that bounces off backwards, toy car going off to the right, V2. Now, the clay and the ball both have the same mass and the same initial velocity when they collide. Now it says, in the paragraph length response, explain in which case the car will have the highest final velocity. In your explanation, reference the change in momentum of the clay and the ball and the relative forces acting on the clay and the ball. So we have to make sure we mention those things and explain using those, or otherwise we won't get full credit. So remember, when we're doing paragraph length responses, A, B, C, D. A is answer the question. B is what's the basic physics that's always true. Doesn't matter about this question at all, but it's always true that applies here. C stands for cite the important information in this problem that's specific to this problem. And D stands for draw your argument together. All right, so let's do that. Basic physics. Well, we have a collision. So for my basic physics, I know we're going to have momentum initial equal momentum final. Okay, what else do we know? So 2, we know that the change in momentum of the clay and the ball must equal the change in momentum of the car. Actually, the change in momentum of the clay and the ball will equal the opposite of the change in momentum of the car, since momentum is conserved. That's important because they ask us to reference change in momentum. And then let's see what else. We do know F equals ma, and we know the third law. So we know the force from the ball on the car will be equal and opposite. The force from the clay on the car will be equal and opposite, because they ask us about the relative forces. C is citing the information, or the critical information, about this particular problem. So what's critical about this problem? Look at the change in momentum here compared to here. The change in momentum of the clay is less than the change in momentum of the ball. The ball goes forward and then backwards, where the clay simply slows down. Hey, that also means that the force on the clay will be less than the force on the ball, because the ball turns all the way around, so the force will have to be larger than that for the clay. D, draw our argument together. So I want you to notice this says do not use equations. So what I've done is I've brainstormed using equations, and now I have to put it into words. So let me just speak through it for you, so I don't want to waste your time writing it all out. So we know that momentum is conserved for the system of the ball and car, or clay and car. We know that the clay has less of a momentum change than the ball. We know that the momentum change of the clay equals the momentum change of the car, and we know the momentum change of the ball is equal to the momentum change of the car. So we know that the car in V2 has to be going faster than for the clay, because since the ball goes through a bigger change in momentum, the car will have a bigger change in momentum for when the ball bounces off the back. Now, what about the relative forces? Well, the force on the ball, between the ball and the car, Newton's third law, has to be larger, because there's a bigger change in momentum, than the force, the relative force between the clay and the car. So the force on the ball is bigger than the force on the clay. All right, all you gotta do is write that out. So if you want to do this on your test, this is what I would recommend. Have some brainstorm area, put your stuff together, and then write it out in words. For our third problem, we have 2 carts. This one's twice the mass of the one on the left. They're pushed together against a spring, and a thread or a string holds them together. You cut the string, and the spring makes them fly apart. Which cart will have the greatest velocity? Well, hey, we don't even have to use momentum for this if we don't want to. The force between these two carts must be equal and opposite in sign. So since this one has more mass, it will go slower. So the cart of M is faster. If you want to use momentum,
then you can just say that the momentum initial equals momentum final. We start with 0, so that means mv for the one on the left plus 2mv for the one on the right. I'll go left and right. And then the m cancels out. And then if we solve it for the one on the left equals negative 2v on the right.
That means it's going twice as fast in the opposite direction. Part B, how does the energy of the spring compare to the total energy of the kinetic energy of the carts? Well, that's where they get their energy. So in part B, the spring potential energy turns into the kinetic energy of cart 1 on the left plus cart 2 on the right. So that's where this energy comes from. It's split between the two of them. Write equations that could be used to calculate the final velocities of both carts.
All right, so I've already done the first one. Conservation of momentum is right here. Conservation of energy is here, so I could do 1/2 kx squared equals 1/2 mv left squared plus 1/2 2mv on the right squared. And I can take this and plug it in here.
And then I could solve it. The one thing that we don't have that they would have to give us for us to completely solve this is we would need to know how far the spring was compressed and the spring constant, because those, it looks like, were not given. But these would be the equations. Energy is conserved and momentum is conserved. Now it says the spring is compressed again, but this time the right cart is held in place while the string is cut. Is this a closed or open system? This is an open system because the disembodied hand of science is holding this one in place. That's an outside force. And so for our system of the two carts, we have an outside force. Momentum will not be conserved. So how does this affect the final speed of the left block? Hey, well, you can see it right here. The spring potential energy now turns into only the kinetic energy of the cart on the left. So that means this energy is going to have to go up from what it was before. So that means the velocity of m increases. Nice. Our next two involve graphs. In this one, we have two carts that are colliding in an experiment. We have a velocity time graph for the experiment as shown. What are the approximate initial and final velocities of the two carts? All right, so this one, I'm going to do orange for A. That's about 5 meters per second. And at the end, so that's the V initial. And the V final looks to be about -2 meters per second. And then cart B looks like it's starting at -4 meters per second as its initial velocity, and its final velocity looks to be about -1 meter per second. All right, so that means for cart B, we have a change in velocity of +3 meters per second. And for cart A, we have a change in velocity of -7 meters per second. All right, this helps us answer part B of the question. It says, which cart has the largest mass? Explain how we know this. Well, since we know the impulse and the force between these two carts must be the same, equal and opposite, Newton's third law, and that this one has a larger change in velocity, therefore it must have a smaller mass, okay? Because the acceleration is proportional to 1 over m, or the change in velocity is proportional to 1 over m. Calculate this mass ratio. Well, we could do that. Let's do it with momentum.
Okay, I just wrote all this stuff out for you. Conservation momentum. MVs for both of them initially, and the MVs for both of them final. I plugged in the velocities for each one. I grouped my mass A on the left and mass B on the right, and then I solved for the ratio MA over MB, and I get 3/7. So that means that A,
mass A, would be 3/7 of mass B, which lines up with what we said over here, that mass A must have a smaller mass. And the last thing is which type of collision is this? Well, we know it's not a perfectly inelastic because they don't stick together. They'd have the same velocity afterwards. They don't. We know this can't be an explosion because they didn't start together and then explode apart. And look at our velocities. We start with big velocities and end with smaller velocities. And since kinetic energy is 1/2 mv squared and our velocities have decreased, we know that our kinetic energy final will be less than our kinetic energy initial, so it's inelastic. Done. Okay, two carts collide in an experiment. The position time graph of the experiment is shown in the figure. What are all the things that you can tell about this collision from the graph? That's a pretty wide open question. That's cart 1, and then there's cart 2. So cart 1, what can we tell? Well, its initial velocity was 0, and its final velocity was, what is that, a slope of 1 meter per second. So we got that going for us. And then cart 2, its initial velocity is 1 over 2, so that's 0.5 meters per second, and its final velocity is 0. We also know that they collide at position 1 at 2 seconds. All right? And we could find, again, the mass ratio, just like we did last time. So let me do that for you quick. All right, so we know that momentum is conserved. Plug in all our numbers, solve for M1. M1 is half the mass of M2. Hey, and that makes sense because M1 was going a half a meter per second, and cart 2 was going a half a meter per second before the collision, and cart 1 was going 1 meter per second after the collision, and they have to have the same momentum. So cart 1 has to have less mass. In fact, half the mass instead, that's double the velocity. And now let's look at some more complicated or involved questions that will be something like you might see on the AP exam. So we have a spring that launches a sphere of mass m at a pendulum. So there must be a spring back here that must have been compressed to delta x, and it has a spring constant of k. The sphere embeds in the pendulum and the two swing upward to a maximum angle as shown. So here's the before picture. It's shot. It collides, it sticks with it, and then it goes upward to a maximum height, delta y, from where we began, and a maximum angle. Okay, so how does the initial energy of the spring compare to the kinetic energy of the sphere before it strikes the pendulum, right here, and then the kinetic energy of the sphere and pendulum after, so right here, and then the potential energy of the sphere and pendulum when they reach the maximum height up here. Okay, well, conservation of energy tells us that we start with spring potential energy here, and for our spring mass system, that should turn into the kinetic energy of that mass, mv squared, 1/2 mv squared. So these two must be the same. Now, we know from conservation of energy that the kinetic energy of m plus little m right here turns into gravitational potential energy here. And that these two, these two should be equal. Kinetic turns into potential. Here, spring potential turns into kinetic. Our issue is right here in this collision. This is a perfectly inelastic collision, so we lose kinetic energy. So we know that the kinetic energy we start with is greater than the kinetic energy we end with in the collision. So the spring energy is equal to the kinetic energy of the ball. It's greater than the kinetic energy that we end up with the ball and pendulum together, and that equals the potential energy of the ball and pendulum after they swing to their maximum height. Okay, derive an expression for the maximum height gained by the pendulum. All right, well, we've almost done it already. So this is mg delta y, but I'm just going to leave it like that. And this is 1/2 mv squared. It's technically m plus m, but the masses cancel out anyway from here to here. And then here to here, I have 1/2 kx squared equals 1/2 mv naught squared. So I know that must be true, and that half cancels out. And then right in here, connecting this velocity to this velocity is conservation of momentum. Momentum initial equals momentum final. So that's going to be mv naught of the ball equals m plus big M v of the pendulum. And so v of the pendulum equals m v naught over m plus big M. All right, so let's string all of this stuff together. This can go in here, right here, and then I can find the maximum height here. So that's 1/2 m v naught over m plus m squared equals g delta y. So this g comes over here, and I end up with 1 over 2g m v naught over m plus capital M squared equals delta y. And that's the maximum height based on things that were given. All we were given is this mass and this velocity, so I just went from here forward. If they gave us this information right here, we could have also used this to find the original velocity and then strung it all together through there if we wanted to. But these were all things that were given. Big M, little m, initial velocity, g. Those are all givens in the problem. Okay, last part, part C. What is the time period of the pendulum? Well, time period equals 2 pi square root of L over G. Hey, I want you to notice the mass doesn't matter at all. So if we had shot a bigger mass or a smaller mass here, or shot it faster or slower, it wouldn't matter. This thing would swing back and forth with the exact same time period because nothing in here will change. So now how can they make this even more complicated on the AP exam? Well, what they're likely to do is say, okay, yeah, but what happens if we double the mass little m, or double the initial velocity, or double big M? So let's take a look. So if we were to double the initial velocity, of this ball, well then that's going to make the height bigger, right? And it should make it 4 times as big, right? Because that's in the numerator. Because delta y is proportional to v naught squared. What if we double the mass m, little m? Well, it shows up in the numerator and the denominator. Okay, so that's an issue. Let me see. That's big M there. That's a little bit of an issue. We know that if we put it up here, that's squared, and if we put it down here, it's added to something. So it'll have a bigger effect up top. So we know that if we double m, so if m goes up, we do know that delta y will go up. It's just a little bit more complicated math-wise. All right, how about if we double big M? Big M's in the denominator. That's easy. So delta y is proportional to that m in the denominator. It's even squared. So if we increase this big M, then the height will get smaller. One last thing I want to point out about this problem is that this does show up on the test sometimes, is when the pendulum swings from side to side, and that's theta, remember that we can find this delta y if this is the length of the pendulum from here to here. It equals the length of the pendulum minus L cosine theta. L cosine theta is this bit right here. Okay? Just remember that. On this one, we have 2 identical blocks of mass m, and they collide, they stick together, and then they slide up this frictionless hill of science. So they're both a mass m. They're colliding. If we include them both, we know that the momentum initial must equal the momentum final.
So we know that we have simply an mva to begin with, and then they stick together, we have 2mv final. So that means the final velocity will equal half of the original velocity.
Derive an expression for the maximum height reached by the 2 blocks. Well, now that I know the velocity that they leave with, so here they are moving together with a velocity of VA divided by 2, I can find the height by using conservation of energy.
The kinetic energy will equal the gravitational potential, so 1/2 mv squared equals mg delta y in this case, because we're starting from 0 height here, and when we get up here, we'll stop. And the masses cancel, so that means delta y equals v squared over 2g, all right? And our v is this, so that would be VA squared over 8g, and that is our height.
Okay, now the blocks are reset and block A is again launched at B, but this time block A stops after colliding with B. Will block B go higher, lower, or the same height?
Hey, that means that MVA before must equal MVB after. They have the same mass. That means the velocity is now the original. So it's twice as big as it was before. So look, delta Y is proportional to VA squared. So if we double that velocity, we should get 4 times the height. So 4 times this, VA squared over 2G would be our new height. 4 times greater than it was before.
Okay, another variation. The blocks are again reset. This time A is launched at B, but B has twice the mass as in case A. Will they go higher, lower, or the same?
All right, well, in part C, MVA equals now, it's twice the mass as it was before, so we have 3 times M, V final. We now have less velocity final. It's VA divided by 3, and we can see that delta Y is proportional to our original velocity, our launch velocity squared. And since this is now getting smaller, this will also get smaller, so we'll not go as high.
For our final problem, we have a ball that rolls down a ramp towards a lump of clay. As shown in the figure, the two stick together and land a distance d from the edge of the table. The ball and the clay have the same mass, and they gave us this height h here and this height h here. All right, so this one's going to turn gravitational potential energy, and then when it gets down here, it's going to have kinetic energy when it gets down to the bottom. What's the speed of the ball just before it hits the clay?
So A, that would be mg delta y equals 1/2 mv squared, cancel, cancel. So the velocity of the ball just before it hits the clay would be 2gy square root.
Part B says, what is the speed of the clay and the ball after the collision? Well, conservation of momentum, look, we've doubled the mass when they hit and collide and stick together, so the velocity should be cut in half. You can prove that to yourself, but the velocity of the block and clay together, or the clay and the ball together, will be half of this. So 2gy square root divided by 2. Part C says, how long does it take the clay and the ball to reach the ground? So here's part C. So this is a kinematics problem.
So y naught y, b, y naught b, y, a, and t. I'm going to call this height y equals 0, and I'm going to call down positive. So I'm going to start at a 0 position with a 0 vertical velocity. It's going to fall a distance h. I do not know the landing velocity. I do know that this is going to be g, positive, downward, and we're looking for the time. So we will use y equals y naught plus v, y naught t plus 1/2 at squared. Let's get rid of our things that are 0. So y equals 1/2 at squared. Plug in the things that we know, and we know h equals 1/2 gt squared. Solve for t, so t equals 2h over g square root.
And that, my friends, is our time for them to fall to the ground from here to here in a nice parabolic arc. In the last part of the problem, the ball and the clay are reset and released again. This time, the ball and the clay don't stick together. And the question is does the center of mass land, where does it land? Does the center of mass land relative to, my English stinks. It says, it should be, where does the center of mass land relative to D? Okay, well, remember in this collision that the motion of the center of mass never changes. So even if this ball stops, the center of mass is still going to land in the same place it was going to land before. So that just means this would land way out here if this stayed here. Or more likely, the ball's going to land here and the clay is going to land somewhere out here. So D is in the same spot. Because in the collision, center of mass, velocity remains the same. Which hits the ground first, the clay or the ball? That's a trick question, my friends, and you should know this. It's the same time because it's a horizontal launch, and so they have the exact same conditions, so the time will be exactly the same. All right, that's it. Our next video will be rotational or angular momentum. See ya.